Hi, everyone. I'm Yuval Peress, and I'll be talking a little bit about Android's CHRE, that is the Context Hub Runtime Environment, and some open source frameworks. And since this is a virtual this is a virtual session, we'll be getting into sensors in a minute. I've attached my GitHub and Discord handle here. Please feel free to reach out if you have any questions, if something comes up later down the line. Quick disclaimer. Most of the things here are still being flushed out. This is kind of a long-term vision, but some things are already implemented and working. I'll try to highlight what is kind of in the works versus what is already done, and so that you know what you can kind of pick and choose from. And obviously things that are not yet done, please feel free to comment on pull requests or issues that are still pending. So I want to start for the purpose of this talk, focus on the sensor framework of the CHRE. And this is just an example. There are lots of other frameworks as well. There's a bit of a naming gap here. Internal to Zephyr, these frameworks are going to be called subsystems. But I want to make sure that everybody's aware of this in case they go to the public AOSP, that's the Android open source project documentation. They'll be referenced as frameworks instead of subsystems. So to really understand when or why we should use CHRE and this subsystem, we're going to kind of build an example together. So let's assume we're all working for some company X, and we're looking to build a new fitness tracker. We'll have some basic sensors available to us. We'll say accelerometer, gyroscope, heart rate, blood oxygen, things like that. And we want to, obviously, highest priority is going to be low power. We want to start off by detecting whether or not the user is active or passive before we start off any more complicated algorithms. During this phase, sensor sample rates can be much lower. Likely, we don't even need all of the sensors on at the same time. Once we know that the user is active, we need to figure out which activity they're doing. So for this purpose, we'll do a triathlon tracker, and we're going to just identify between swimming, biking, and running. So we'll have some pattern detection for those three things. Once we've figured out which activity we're actually doing, we'll start collecting metrics to help the user perform better, recover, and whatever else they might need to do. So how do we design this and build this? Well, there are a lot of components. This is an example of just a small subset of what we would have to do, right? You would have this module here that just detects whether you're active or passive. It uses some composition of these sensors and broadcasts an event for that. We have an activity detection that differentiates your running, swimming, and biking. And then in the assumption that we're running, here's some stride calculation, cadence, power, things like that. So as you can see, the scope here is very, very large. And these modules are somewhat compartmentalized, but also have some dependency on another, right? This one will never run until this one broadcasted the active event. So here comes the concept of Nanoapps, which is really what CHRE is all about. It's the differentiation of division of labor. So the top level view, and in this example, we have two different processors on our board, but that is not a requirement for this by any means. We have the CHRE system here, the sensor subsystem here, and several Nanoapps that might be running here. And what you can effectively envision here is that CHRE is responsible for the runtime of these Nanoapps. It loads, unloads them, possibly dynamic, although that is further down the line, that is not implemented yet. It can start and stop these Nanoapps at runtime. The Nanoapps are just compartmentalized units of logic. They can register to receive events, and they can broadcast these events. So the CHRE system is effectively a pub subsystem. It also includes some request arbitration, which we'll get into a little bit later. And it is responsible for also the runtime environment of these Nanoapps. The final thing is right here, there is a host link, which is effectively how Nanoapps will communicate in this example off chip, but that is again not a hard requirement. The host link is implemented by the application, the Zephyr application, and is allowed to effectively just route the messages, the outbound messages from Nanoapps to wherever the application needs them to go. So zooming in a bit, we want to take a look at how Nanoapps interact with the subsystem through CHRE. So here, Nanoapps using the CHRE API, which then talks to these different subsystems. Now, we'll start off with implementation for just the sensor subsystem, but obviously any board or any team that is interested in these other subsystems, such as GNSS, Bluetooth, audio, Wi-Fi, and WAN, you're welcome to obviously implement these or request some guidance, and we'll work on this together. Sorry. Nanoapps are effectively going to make requests from the subsystems through CHRE. CHRE is going to arbitrate these and pass these down to the specific subsystems and provide the data to the Nanoapps. So let's talk about why we're doing this, right? This is the biggest thing, is we need to have a good solid reason for adding all these different layers. And really, the idea here is to allow the developer or the company to really focus on the features they want to build, instead of dealing with how they're going to manage event delivery of data, how you're going to manage getting all the sensor data that you want, or configuring the sensors to the correct state of your program, and making sure that two different modules with two different requirements get the data that they need. And because of this clear distinction, it's much, much easier to test the features that you've built. Nanoapps have a very tight API, 3 functions only. We'll get into those in a little bit, that interact with CHRE. So you can mock the entire CHRE system and test your Nanoapp very, very easily. So some example of Nanoapps, just to give you kind of the feeling for what you can do with this. You could write a fall detection Nanoapp that would simply depend on an accelerometer, right? You would look for 0G for some duration, followed by a strong spike. Car crash detection would similarly depend on an accelerometer, but could also include an optional dependency on the audio subsystem. That would make the detection more reliable. Activity detection, which we've seen just recently, glass break detection, depending on the audio system, geofencing, right? We might want to wake up the application processor when we've reached a certain area. And while Bluetooth and Wi-Fi scanning could leverage their respective subsystems, the general application events when, sorry, the Bluetooth and Wi-Fi Nanoapps, effectively you can imagine background scanning, waking up the application processor, letting you know that you can migrate to a stronger Wi-Fi connection, or a new Bluetooth device was detected. So effectively you're looking to save power on these. Overall, these subsystems provide a clear separation of responsibilities, and that's really where the power comes in. The inner workings are really simple. We have a start and an end event, and a handle event. The Nanoapps are registered with CHRE using a C++ Nanoapp class, which will very rarely actually have to interact with. There's a couple of macros that help us wrap all of this up, and you can write all of your logic in C. So let's see the workflow here. So here's a bit of a graphical workflow of how a typical Nanoapp would be implemented. CHRE is going to load the Nanoapp, call the start function. During this phase, the Nanoapp is going to get a list of sensors by type. It's going to say basically, I want to get a list of the accelerometers from CHRE. Then once we've picked one that has the capabilities we want, we're going to request events. At this point, the start function is done. While the event loop is running, we're going to get calls to our handle event from the Nanoapp. We're going to process it and possibly broadcast a new event out of that. When the time comes, CHRE is going to call our end function, which will terminate the Nanoapp. Now, keep in mind, if you are statically linking these Nanoapps, it is possible to also turn on a bit that will disallow CHRE from effectively turning off your Nanoapp. So you won't even have to implement this. In that case, that is probably the majority of the Nanoapps that we'll see in the embedded world for Zephyr. But there are larger applications where Nanoapps might be started and stopped depending on the current state, and even offloaded from RAM to save space. They can be loaded dynamically. So how is the loading done? We mentioned that this would be super easy with a macro. It's right here. There is a CHRE static Nanoapp init. You give it your name, an ID, a version, and you give it the permissions right here. And there is some binding, and this is where it's not, you don't see obviously the links to these here. This is still a bit flushed out, not flushed out, and you can see in the example right now, I didn't want to put it in the presentation because it might change quite a bit. I'm still tweaking some of this, but effectively all you'll need to do is call this macro, which again, some of the arguments here might be tweaked a little bit. So we mentioned request arbitration, and this comes actually in two different layers. CHRE includes the request manager for arbitrating between Nanoapp requests. That means effectively if we have two Nanoapps that are running at the same time, one might request the sensor to run at 100 Hertz, the other one at 200 Hertz. The arbitration there will say, well, we're going to just run at the higher rate at 200 Hertz because that would still satisfy both requirements. Similarly, the sensor subsystem, which we'll get into at the latter part of this talk, is going to also contain an arbitration system. And the reason is because the subsystems actually aren't, they don't require you to run the CHRE system as well. You can choose one or the other or both. So we'll do a quick dive into what the managers actually do. Oh, okay. Right, so effectively they help us support multiple clients. So here you can see what the example that I gave. Client 1 requests 100 Hertz. The subsystem talks to the actual physical driver and configures it to 100 Hertz. We get another request for 200 Hertz, and then the second client basically turns off, and the subsystem is required to bring us back down to 100 Hertz in order to conserve power. And when there are no more clients, obviously shut down the sensor. So let's talk about the host link a little bit. And in this case, again, the example I've been giving is communication off chip, but that is not a requirement by any means. So the Nanoapps themselves effectively have a single API. It uses the host message struct with a raw buffer, which is just a simple wrapper around standard C array. You give it the size and a pointer to the start of the array, and you pass that into the CHRE send message with permissions function. Now, the application itself is going to need to set this kconfig value here. The default is 4,000 bytes right now, but again, we might change that. So please make sure you set that yourself. And you'll need to implement what the host link function for send message and flush messages sent by Nanoapp, and you get the Nanoapp ID. It's a UNT32 here. And I want to give a quick slide here about pigweed, which is not really a framework, but it is a set of libraries that we've ported to Zephyr. And this is actually really, really neat. There's a ton of logic here that is pre-done for you if you are looking to offload some of it. We're going to focus on RPC and HDL real quick here, but you can see here there's a lot that's been done and even more on the way. You can grab the code by basically doing copying this repo right here and adding it to your Zephyr modules, enabling the entire pigweed library here, and then choosing specific pigweed modules here. And This allows you to write kind of portable code that is not specific to Zephyr. So if you do have to choose between the two, but in addition to that, it does bring in a couple of libraries that don't already exist in Zephyr. So in this example, right, there is this RPC and HDLC libraries, which are particularly useful. And what I would say is, if you haven't used RPC, I highly recommend checking this out. There is a sample project for pigweed. But the key benefits here is that it's very easy to extend and iterate the communication protocol. It uses protocol buffers. The abstraction provided by the tool, since it's possible to, the abstraction allows you to generate clients in C++ and Python, and currently Java and TypeScript are in development. And what this means is that if your application, if the embedded Zephyr application is initialized as the service of the RPC, then what you can do is, in testing, mock out the component that actually sends things off chip, maybe that's a UART or BLE or whatever other means you have, and swap that out maybe with a regular socket, and then communicate to a Python client that actually drives your test for black box testing. So this provides a very, very nice benefit also for testing. If you want to get a little more information about Nanoapps, here are some additional resources. Obviously, you guys saw that the slides are, the PDF is available on the, what's it called, Sketch page, so you can get these links later on. So let's talk about the actual frameworks / subsystems. And they provide the critical features for Nanoapps, but this is really important, is they can be used as standalone. So you don't have to use CHRE in order to use these subsystems. So the sensor subsystem effectively can have two clients in this case, right? Both the application and CHRE, which means this can be completely removed here. It will be added with a simple kconfig. This will be done fully upstream. So you can just enable this sensor subsystem. Naming is still under development. And one of the other kind of features of this is that you can very easily configure this with device tree, and this allows you to avoid a lot of boilerplate logic for how to configure the sensors for your runtime. Once it's implemented, the subsystem will handle a couple of things for you automatically. Things like timestamp spreading when you have hardware FIFO data. The subsystem is also going to provide you several virtual sensors. And keep in mind, if we don't have the virtual sensors that you need, you can always implement them as CHRE Nanoapps like you saw before. The final feature here that is not yet slotted, but is considered to be added eventually, is hot plugging sensors. But we're going to try and make sure that we design around it so that we can do it later on. Sorry. So let's talk a little bit about physical sensors. Here's an example with a couple of, two physical sensors. And the idea here is that the sensor subsystem allows you to focus on specific sensor types. They might both be backed by the same actual physical sensor here, but they don't need to be the same node effectively. So your application might want to narrow down and only use one or the other of the specific physical sensor. It also provides, in this case, our rotation matrix. So in case you have some limitations of how your board is laid out, it's possible that you want to standardize all of the sensors on the board to the same axes, and the subsystem will allow you to do that simply by including it right here. And again, this is a bit under development, so don't hold me accountable for how this might end up right here. The features will be there, the how it might change. We also mentioned virtual sensors. So in this example, we have 3 sensors. We have a physical step counter using the BMI 160 and a virtual step counter using the same BMI 160. And you can see that they're very easy to configure and effectively instantiate. The there's no real practical use for having both of these obviously enabled at the same time, other than maybe testing how well your algorithm works, right? You want to flash this to a board and walk around and see what the difference is between these two. Another example here is a lid angle calculation, which uses two different accelerometers to calculate this. And again, you can see using two simple P handles, that's all we really needed. So if you want to write your own custom virtual sensor, that is also a feature that we're looking to do, to enable, I should say. Sure, you can do it as a Nanoapp, but again, we don't want to force anyone to have to use the CHRE, although I highly value it and I do think it is a great tool. So here we're going to build the drop detection Nanoapp effectively, but as a virtual sensor. This is going to emit an event when the device was dropped, so it's going to have its own custom sensor type. And effectively what it's going to look like is this for the end user, right? The actual logic of it is going to simply register that it wants to use this accelerometer underneath, under the hood, and it will register events just like any other client to the sensor subsystem. So doing it this way allows you to also have multiple instances of the same type of sensor. So you might have two different drop sensors based on two different accelerometers in this case. So if you're wondering what sensors you can expect out of the box, well, the first thing we're going to do is implement the CHRE sensor types that you have. So there are a bunch of physical sensor types, such as accelerometer temperature, pressure, these things. They also include like hinge angle, which are the virtual sensors. As a fast follow, we're going to go ahead and implement all of the HID sensor types. So you might see accelerometer 1D and 2D added to this, and a couple of other kind of activity detection type things. The final step here is going to be the leaving a range of sensor types that are available for the application developer to add as their own custom sensors. And if you find one that is particularly useful, it's as easy as sending a pull request to push it and promote it to Zephyr proper. So how do we use it? Again, don't hold me accountable for this, but this is the general workflow that you're going to have. The obvious naming and API might change a little bit, but you're going to have an open, which will allow you to register some callbacks object that you want to get all your callbacks from. You can get a list, populate a list, and get the size of number of sensors, which will iterate through. You can then iterate through, find whichever sensor you're interested in. Then you can configure the sensor with the interval and latency, and this is where arbitration comes in. So you might have multiple clients actually try to configure the same sensor handle using two different combinations of mode, interval, and latency. And then finally, you can expect your callbacks in this kind of format. The sensor info index is effectively the index into the list of the sensor providing the data. And from that list, you can get the type, which will allow you to cast this void pointer. This callback here is going to be basically handled inside the callbacks struct. So that's how that is looking. And again, the API here is very, very likely to change. It's still in the early phases. You can actually see here that we didn't, I didn't even include here for the configure sensor passing in some kind of client handle to make sure that we do the arbitration correctly. So even on this slide, there's some tweaks that need to happen. So a quick mention for the other frameworks that CHRE supports, right? We have audio, and you can imagine doing hot word detection, alarm custom, gain for the audio volume, background scanning for Bluetooth, Wi-Fi, geofencing we mentioned. You can get the basically events generated when cell tower information changes, so you'll be able to write Nanoapps that wrap around that, or do get those directly in your application. and we'll implement these. They're unscoped, so we'll implement these as needs come up. And that's it. I left 5 minutes for questions, and it looks like I was just on time. So I'm gonna, yeah.
I'm not sure if people can unmute themselves directly to ask questions, or I'm not sure actually. If that's not the case, then please post a question on the Discord channel, and then oh, there we go. So
Yeah, I see.
you can see it, Yuval, yourself.
Yeah, I just turned it on here. I see. Is this compatible with format string dictionaries? So let's see. I'm not actually familiar. Can you elaborate on this a little bit? I'm not sure what you mean by format string dictionaries. I'm sorry. The only thing that comes to mind is like Python dictionaries, but I don't imagine that's what we're looking at.
No, I think this is so dictionary logging is when you don't output the actual string, but rather some identifier. So and then it's the actual logging string is stored elsewhere.
Yeah, I think there is actually a pigweed library that tokenizes string in order to reduce your memory footprint, and that might be, I guess, what's being asked around here. So yeah, there is a pigweed library. I haven't finished migrating it, and it's kind of been on the back burner because it's not a hard requirement. But the pigweed team is always super happy to get other people to pull requests effectively. They use Garrett. So feel free to kind of model how the rest of these modules have been done, and you're welcome to do it. It is slotted to eventually be done.
All right, Yuval, sorry, thanks for answering that anyway, but this was a question on the other track. The problem is both tracks are on the same Discord channel. So the other track, which is happening in parallel now, was about logging, and hence the the question about. All right. So this was. We do have a question now on the chat of Zoom, the Zoom chat. What is the code set contributed by the code of CHRE? So how big is CHRE once compiled?
I see. So CHRE itself, and man, I should have actually gotten some of these metrics. It's a little hard to gauge because obviously it depends on what platform you're building it for. I believe that, man, when I built it for native POSIX, it was in the order of, I want to say it was in the order of just a few kilobytes. And again, remember, CHRE is just the runtime. So all it does is arbitration. So I want to make sure that everyone's aware of kind of how this is done, is the distribution of work here, right? Most likely the sensor subsystem is going to be actually a larger code, basically code base. But the key of this is the when to use this is if you need these features effectively, I want people to be able to avoid having to implement these. So I would say, the actual answer, there's a real number, but I will also argue that the number is actually irrelevant, because if you use CHRE because you needed arbitration for configuration and you needed event delivery, then you're using the features that CHRE has implemented, meaning if you didn't use CHRE, you would have had to implement these yourself. So the beauty here is if there are any optimizations that come down the line, your team is not responsible. So you not owning the code is actually a really big plus in my opinion. So in that sense, if you want to think about it that way, the actual code size cost is zero, because if you use these features anyway, you would have had to implement these or use another third-party application. So that's at least how I'm looking at this. I can probably try and find out, and sorry, I'm gonna use the last name here because I would feel bad mispronouncing the first name. Gundi. I'll do my best to. Okay, sorry. Thank you.
Thanks. So we have another question that's very generic on Discord. Would you expand a little on what is CHRE and what the motivation is to include it on a Zephyr project? You've touched upon that, but maybe you could re-summarize it in maybe under a minute.
Yeah, sure. So effectively, the motivation is, I believe that most applications will want some basic features such as this. If you want to sell Zephyr to a startup, for example, I've worked at a couple of startups, and time to market is the most critical thing that you can basically argue with these people. And if you want to tell someone, hey, you can just build the Nanoapp, right? You don't have to worry about event delivery, arbitration, timestamp spreading, all these different features that you would normally need. You just need to have your Nanoapps effectively, the processing, the actual core logic that you want to focus on, and it's easily testable. That's when you would want to use this. And what I'm really hoping is this is a catalyst for people to say, oh, yes, I want to use Zephyr because the time to market is drastically reduced effectively.
All right. Thank you. Let me check if we have any additional questions. I don't think so right now. Okay, so we don't have any more questions. Great. With that, then we'll close this presentation. And with that, the track B on the virtual talks track today at Zephyr Development Conference. So thank you very much, Yuval, for presenting today and answering the questions. And everybody have a nice day. We're ending the broadcast here. Thank you. Bye.